So how many satellites we have here? 4, because I have 4 rows. And how many variables I have here? 4. I have 4 columns. That's the x, y, z, and the b. See? X, y, z, and the b. And then you add this noise. So this gives you the measurement model. The measurement model right here. That's the important equation we start with. And what you know this by the measurement. From the last distance to the current distance, you got this data row. Why is a vector? Because you have 4 of them, right? 4 satellites. And this H is the geometric matrix. And this is the 4 variable change. And here is the noise. So what is the least square error method? We need to minimize this. We need to minimize this error times itself. That's the least square. We did this in the linear regression, right? The linear regression, we do the same thing. How do you know this line is the best? You measure all this deviation and you square the distance. That's the same idea. So let's do the math. This total error, this is the square of error, the sum of square actually, sum of square error equals this noise data itself, which is a scalar. And if you look at the noise equals the measurement minus this prediction. Keep in mind that what you do know is the x and the b. And then this is the noise. So put in this side equal this. This prime is the transpose, means the turnaround, times itself, make it a square. So look, what is that? That's 1 by 4 times 4 by 1. And then it's a 1 by 1. It's a number. In the end, it's a number. Now, how many variables you have? 4. X, that's 3, and the b at 1. Then you take the gradient to this scalar function. This e is a scalar function for 4 variables. You take the gradient, that means you're going to take the derivative to x of e, take the derivative to y, take a derivative to z, take a derivative to the b. And then, of course, you want this to be 0. That's how you find the critical point, right? So take the gradient, you use the product rule. That is the gradient of a, b equals gradient of a times b plus a times gradient of b. Same as your product rule in calculus 1. But don't switch the order. If you switch order, nothing make sense. So take this is a constant. You know it. That's your measurement. And this is a constant. Then you take the derivative to itself. Now, this x is just x minus x0, y minus y0, b minus b0. Now you take a derivative to x, that's 1. And that's why you take this derivative. Then you got the 1 here. You got the negative h. That's all. This all gone. And times this, right hand, that's the second one. Let me just write down this. Now this is the data step. Take the derivative to the second one, and then you keep the first one. You keep this, and then this derivative is the same as negative h. Well, since this is symmetry, you really got twice of this, equals 0. Now these two are the same if you look carefully. Oh, that's 0. Yeah, that's the same. Then you get this equals 0. Now you can put in two sides, take a negative 2 away, and then this h prime delta p, the measurement, that you all know, and this side you don't know. So what's that? That's just like what you learned before, ax equal b. You can solve that. How? Take the inverse. And then we just put the inverse on both sides. This is a square matrix. And then you get this. And that's your solution. Look, that's your position change, your bias change, equals the satellite geometric matrix inverse times the geometric matrix times data rho. Well, what does that mean? Now, write down this back. That's the current position, the current bias, equals the previous position. The current means t equal k. The previous step is t equal k minus 1, like the gamma filter. So the current position equal the previous position. That's how you get the delta, the change, plus your solution of the change. Whoa, you got it. That's how you directly to do the computation. We call it least square method. Well, actually, if you read other reference, I would add a little bit of words for you. This h, k prime h, actually is the Hessian matrix second order. And it's the same as Newton's method to solve equation. You remember what we try to solve is where the gradient of the error equals 0. And what's the Newton's method if I want you to solve this equation here? Newton's method is this, right? Take one derivative, find this, and take one derivative, this. Your xn equal xn minus 1 minus fx over f prime x. That's Newton's method. Do you remember that? And then if you want to do the change, then we have the same idea. You want the gradient equals 0, then you really try to get this gradient is 0, then it's really the gradient of this error times the Hessian divided by the Hessian of the error, second derivative. So the Newton's method could be, if you go to the second derivative, you want to find out where is the f prime x equals 0, then you do this, see, x prime, x double prime. And we need to get the gradient equals 0, then you get the gradient over the Hessian is really the second order. We did that. That's why this is also sometimes called the linear quadratic equation. That's just for prepare when you read other book, like the book I referenced. Anyway, go back to the least square. So how do we do it? We start a guess. Doesn't matter where you think you are. You can think you're on the center of the earth. You want to make a much better guess. And then you use this formula 3-4 times. Actually, you can pin down your own position in a few feet. Usually it's 3 to 4 times. Well, let me just give you a little diagram to show you. You can read this. In that input, you need the satellite position, which is monitored by all the ground stations. You need to have the error model. That's what we are talking about. You need to have an initial guess. You think you are in the center of the earth, fine. And then you input into your either gamma filter or the least square method, and then you find your result. When you do simulation, you can always compare what you find and what it really is. That's the whole idea. Well, now let's go to the